formulation. Yes, most of you are familiar with it, but it will be used by many of the lectures. So. And then I will try to convince you that I will give a general formulation of the many-body problem in terms of creation and non-relational structures. And then I will try to convince you that you have an algebraic formulation of this many-body problem, and that in specific cases you have solutions of the many-body problem, analytic solutions of the many-body problem. Okay. And this has to do with the notions of symmetry and its extension, dynamical symmetry, and I also will mention something about partial dynamical symmetry. So I will develop this sort of in general, and then in the course of this lecture, by several of the lectures, these notions, especially dynamical symmetry, they will be discussed in detail with many examples. I will illustrate the notion of symmetry with isospin, and we'll discuss isospin in detail. So that's what will be after the coffee. Okay, so let me remind you about the problem we wanted to solve. And we have a Hamiltonian. A particles, kinetic energy. Then I will, here there is no reason, although that doesn't exist in nuclei, but there is no reason not to add an external one-body potential. And plus, etc. Okay, this is two-body, maybe three-body interactions. Right. So what I will say here, it works if you have a one-body potential or not. It doesn't matter. Okay, so that the step towards second quantization, or also the use of these algebraic techniques, many-body problem that can either have one or not. For instance, if you have Bose-Einstein condensate, they usually will be confined in an oscillator-like potential. An external potential that confines the condensate. Okay. Now, as I said, this is a difficult problem. You can have, let's call it an independent particle approximation where you neglected this term eventually. You introduced the mean field, so you had an additional mean field potential which you subtracted from the interaction to define the residual interaction. So you in this formulation you would have a single particle potential, right? It's for one particle, right, with a one-body potential. Eventually, this might be this one, or this might be something which has a mean field. This defines a basis. Okay, as I discussed yesterday, it defines a basis with some labels alpha, and so depends on those. Okay, so what you do now in second you say, well, I will associate creation operators, and so I will introduce a creation operator which is characterized by this single particle index alpha here, and this, I can also use this notation, so get notation, so the alpha will go in get, and so it is coming from a creation operator onto the vacuum, that is a vacuum. Okay. And this corresponds with a single particle wave function. I mean, the correct way to formulate a single particle wave function will be this kind of bracket. Okay. And the same thing for annihilation operator. So we have the vacuum annihilation operator, this is the emission conjugate of the creation operator. This is alpha. Okay. So this is associated with star. Definition of this. Okay. So this can be done for fermions or for bosons. Okay, in this problem that we treated yesterday, of course we had fermions. Okay, you will see in the lectures, for instance, of Jan Joly, he will have something that involves bosons, and so then these are boson creation operators and annihilation operators. So the difference is just, I will consistently denote the following. So A dagger alpha, A alpha, for me those are fermions. And B dagger alpha, B alpha, they refer to bosons. And if I don't want to say what is the nature of the particles, then I will use the notation C alpha, C dagger alpha is alpha. Okay, and you know, imagine very well that the boson satisfy commutation relations and the fermion satisfy anti-commutation. So this is basic. Let me move this down. So this is the anti-commutator. So this is delta alpha beta. So the anti-commutator. Okay, to annihilation of two creation operators. 0, the same thing for the bosons. In this case, this is the commutator. This is defined to be alpha beta, and then the commutator will be annihilation operators, the creation operators is 0. Okay, so this will go on. What is the advantage now? This is when you go to many body states. If you go to many body states, remember yesterday we introduced our antisymmetric wave function. So it was a wave function that was in, let's call it here, n particles. And so it was in quantum state alpha 1 to alpha n. So it depends on the n particle coordinates. And so this now can be, if you make this association here for the single particle states, this now can be conveniently written as A dagger, if this is for fermions, okay, alpha 1, A1, alpha, A alpha 1, yeah, alpha n acting on the particle. So the trick is that the antisymmetry of the wave function, so if you remember, this was rather a big expression, later in turbulence, this property of antisymmetry is conveniently written in this way, and the antisymmetry of course follows just from the anti-commutation rules of the operators. Okay. In the same way, so this is the representation in second quantization of Slater and turbulence. And in the same way, you can do this for bosons. And so for bosons, you would have a state like this. Okay, and so the symmetry of this state follows from the commutation relations. And this is actually called the permanent. The Slater permanent.
Is there any difference between these curly brackets and these third brackets?
Between?
Yeah, the curly brackets. For A alpha you write it in the curly
Oh,
brackets.
yes. So you see, the curly brackets here, they have a plus sign. This is the anti-commutator. This is very important. The square brackets, they have a minus sign. This is the commutator. And so everything comes from these two signs. So the properties of antisymmetry of this guy, it comes from the fact that you have here plus signs and here also, the curly brackets. So the curly brackets refer to anti-commutation. Yes, this is an
Pete,
yes.
don't you want a dagger on the last bit?
Oh, yes. Good. Otherwise it's zero. Maybe I forgot to write this. Yes, I forgot to write this, but another property is of course that the annihilation operator acting in the vacuum is zero. And so the annihilation operator, the creation operator is in this way in the vacuum. And so you have a set of simple rules, right, relating to the vacuum and then creation and annihilation operators that commute to anti-commute. And so the whole business of symmetry and anti-symmetry comes from these rules. So that is your second quantization. So now what we want to do is to rewrite this problem. This can be proven, huh? So that if you make all those rules, that these states have the proper antisymmetric or symmetric meeting. Okay, so now how do you can represent now all operators in second quantization form, and so the second quantization form of this Hamiltonian. This will be something like let's do it in general. Okay. So mapping is quite logical, so I do it with C operators because this can be done for bosons just as well as for fermions, but of course in the shell model these will be fermion creation and annihilation operators. In the boson model this will be boson creation and annihilation operators. And so here you have a summation over a set of single particle states. Now if in principle, so this, you have an infinite number of single, or you can have an infinite number of single particle states in most of the applications, so this is an infinite sum. Right? And so what you will do in practice is,
Excuse me, like in the case of this boson-Slater, shouldn't you write also in each bit dagger, like to the power n alpha 1
yes,
and n alpha 2 and so on?
yes, this could very well be, but I haven't said here anything about whether these indices are equal or not. Okay?
Oh,
I just said I have n bosons. The anti-commutation relations for the Fermions will make sure that if two indices are the same, the state is zero. Whereas the commutation relations, they allow anything. Okay? And I just wanted to have here n operators, but if alpha 1 is alpha 2, then it's also alpha 1. Okay. And so now you have single particle, this is the interpretation of that, is these are the single particle energies. And these are related to the two-body matrix elements. So I wrote it here a little bit schematically. I didn't want to get into coupling the particles to a given angular momentum, so that you have two-body matrix and you have a specific angular momentum. So this I didn't do. It's just a schematic representation of the same Hamiltonian, and so you will see in many examples we will specify what those single particle energies are, how the two-body matrix elements can be written if you want to have operators here with specific angular momentum or specific isospin, whatever symmetry you want to impose. Okay, so the important point is that this is just an equivalent formulation. It's much more convenient to work with this kind of formulation because all the questions of symmetry and antisymmetry can be dealt with this Slater.
Excuse me.
Yes.
What is the meaning of second in second quantitation? Just I want to know the meaning of second.
Yes, the terminology. Why the name?
Yes.
It's a bad name. It should be something like occupation number formalism. Second quantization is used also in solid state physics, for instance, and there it's more proper. So you see sometimes wave functions with daggers. So that is the proper second quantization. This I think in the outline I called it occupation number representation, because that's basically what it is. I don't think you should give it any fundamental importance. This is like you do a first quantization and then you do something fundamentally different to the second quantization. It's not. It's an equivalent formulation.
Maybe you should also explain the order of annihilation operators in the two-body term.
These two you mean. Oh. Yes, because you see they act in a specific way on the state, right? And so that means that the first action is from gamma, right? So the first, I cannot talk about particles, but so the first one, the first operator that will be encountered is gamma, and that is why I put the gamma and the delta in a different order. It's not such an important point because the only thing I say here, these are quantities that are related in the two-body matrix, related to the two-body matrix elements. If I want, you will see that there are some factor square root of j plus 1 which are involved also, so they're not directly the two-body matrix or the parallel. So if you wish, you can put this order alpha, beta, gamma, delta, and then include the sign in the definition. This is the normal, and you see also a factor 1/4, because normally you have some order where alpha is smaller than beta and gamma is smaller than delta, because if you have the permuted states will be identical, and that's where you have this form. I don't want to go at this point into the details of the definition of those organs. Okay, the summation, that is an important point. Here we have a summation over A particles. A can be big, but still it's finite. Here we have a summation over states, right? And so in principle we have an infinite summation. And so the picture you should associate with these things, so it's again, we have a potential, so this alpha scale were defined by a single particle potential, right, with some levels which are labeled by alpha. And so now you will have a number of particles, n particles, let's say. And in principle, this is for an harmonic oscillator, this would be an infinite number of states. This you cannot do. So you always make some selection of what are the states you want to include. Right, this. Well, I don't want to go about very space here, but these are the states that you want to include in your space. So you will have a summation over some subset of states. Here the available states, let's call that omega. Okay? So you have n particles which should be distributed over omega available states. For instance, if you are here with the 50 to 82 shell, omega will be 32. Right? You have 32 available quantum states. And then this is a combinatorial problem. If you have fermions, the number of ways you can put n particles into omega states, but you should not put two particles in the same state. So that's a combinatorial problem. This is for fermions. So this is n factorial or omega factorial. Okay. And so this gives you a rough estimate of what kind of dimensions you will get initially. Let's do this. What was your Lucius?
154 scenario.
154 scenario.
It's not mine with this.
Well. We will need somebody with a calculator. Okay. 154. 62. 92, right?
Yep.
So, we do the neutrons and the protons separately. So the neutrons are in 50, the protons are in 50 to 82. So the omega is 32, and we have 12 particles, right?
Okay.
Then the neutrons, they are in 82 to 126, so that's 44, and we have 10 particles.
That's close to
So, is there anybody with a calculator?
yeah. It's close to the limit. What do they get to?
It will be bigger than this number.
Why did you flip the order?
It says 5.6, 10 to the power of 7. 10 to the 5.6, 10 to the power 17.
17.
Okay.
Yes, I mean,
Would you expect that? I might have messed up somewhere.
So this is completely. I mixed the two up, so it's omega. This is usually the big number goes upstairs, right? Right, because you must have more available quantum states than you think.
Try it again.
So then the decision is 17. You got
14.
14, right?
2.89 instead of the 14s.
So you have a factor 1000.
Nothing.
Like 5.6 into 17.
Why is this? Does anybody have an idea?
5.6 into 17.
Yeah.
You got the same?
Excuse me?
5.6 into 17.
Yes, yes. Right? So, but why is it bigger than the number which was quoted by Piet?
Using doublet,
What?
there are some of them are doublet. You can read some of them out.
Let me remind you what he did. He was counting the number of 2 plus states, right? So here, what do? You really count all states, right? That is any m, the m can be 0 to whatever maximum value it can have. Right? And so it's even a larger, because shell model calculations would like to try to do this in the m scheme. In the m scheme, the dimension would be larger than what was obtained by Rick, but it will be smaller than that, because this is for all m's, m0, m1, m2, and -1. So we have all possible. And so this is a typical reduction. I mean, if you want to have an idea of what is the shell model space for the nucleus, you do this calculation and then you divide by something like 100 to 1000. You will get a reasonable estimate of dimension. Okay? And of course, it's very large. For bosons, so actually the dimensions for bosons are worse, because you can now, so again, let's assume you have n bosons, you can put them in omega available quantum states, but now you can put many bosons in the same quantum states, and then the formula is so that again, this will be all the states, right? If you look at specific m states or specific spin states, this would be,
So, excuse me,
yes.
can you maybe please explain again, how do you get these omegas for the,
This one?
yeah, for the estimation for the
Oh,
moment, for
maybe
example?
I made a mistake.
No, I'm just curious how,
Yes.
I didn't get it how you
Yes.
get them really.
So this is for the protons. This is for the neutrons.
Yeah, I got it, it's just how many spaces I have in the shell.
Yes, yes.
Yeah, okay.
And I do the neutrons and the protons separately.
Yeah.
Ah, yeah.
And that's easy.
Yes. Because, okay, you can also do it in neutron proton formalism, but then you have only the number of particles which will be used. So, will not be definite nucleus. Okay.
And when you're close to a shell, you kind of hold up to,
You can what?
for example, if you have,
You count holes past the
do you count the holes?
Oh, this,
No, I mean, when you're close to
yes, yes.
a closed shell, but you're below it, you don't count the full shell, but you count just the numbers up to the...
Yes, but this formula, if you see, if you look at it, is symmetric, right? Symmetric. It implies that once you are above mid-shell, these two are interchanged. So you will get exactly the same dimension in terms of fermion particles or fermion holes.
Yeah.
Right? It has to be symmetric. It's not the case for this one. I have my two-body problem. My many-body problem, here it is. So I try to solve this notorial. I try to convince you that this is a hard problem, so because if you have a reasonable sized Billion space omega and a considerable number of particles, you get to numbers of this order, so very large. Okay, and so this is one of the problems of the nuclear many-body problem. So this is the size of the Hilbert space. And so, in principle, in this space, you have to construct your Hamiltonian. It will not be diagonal, so you have to diagonalize the Hamiltonian in a huge Hilbert space. And that's one of the problems of the nuclear many-body problem. Okay. So now what I would like to do is to say that there are situations where you can do this problem by algebraic techniques. And yes. Yes.
The number of ways that you can which you can put n bondings beside the omega space, we should be able to understand why that this is a fashion.
Yeah, this is, I would not be able to, I have known how to derive this.
No, okay, it was just for me to understand.
But this, okay, I can think about it, but I find it again, it's not such a trivial, here it is a trivial derivation.
Okay,
But that one is yeah, I could not be able to put it.
You just think of your different states as like barriers, so you have a set of omega plus and particles, right? Do you know this thing I'm talking about? And then you add in partitions to your set, and then you take combinations of the partitions and the particles.
Well, it's maybe easier to think like you have a chain of balls lying next to each other, and you have a certain set of sticks you want to put between them to intersect them. So this gives this formula.
Of course, it doesn't mean you can derive it, I agree. But here, so the matter is trivial, that one is more intricate. Maybe you should look at this afterwards.
It's good.
If you can do all the problems, then maybe try to do this one as well. Okay, so an algebraic solution. So what do? You introduce operators which I will denote as alpha, beta, and these are just bilinear combinations. So we have a creation operator alpha and an annihilation operator beta. And so I would like to stress these are C operators. So this can be done for either bosons or for solids. Now I wrote down commutation, anti-commutation relations to the A for the fermions and the bosons. And from this you can derive this is a commutator, right? So although you might start from fermions here, right, you still can show that the commutator of these bilinear operators closes. Right? This is the algebraic structure, because you have defined some operators here. You take the commutator of the operators with all the possible other operators, and you see that you find a closed set. Right? So this structure is called a Lie algebra. Remember, I was alpha and beta also. They run over all the available single particle states, so from 1 to omega. And actually the Lie algebra, which is associated with this, is U omega. It's the unitary algebra in omega dimensions. I'm not going to give a course on Lie algebras here. It's sort of easy to understand what this does. These operators, they annihilate a particle in a beta state and create one in an alpha state. So this is a transformation from beta to alpha. And it's a unitary transformation. You have omega objects, so it's a unitary transformation in an omega dimensional space. Okay. And this might seem to be a trivial thing. It is rather easy to understand. But you see, for instance, the Hamiltonian here. This is immediately a bilinear operator. This one, it has C dagger, C dagger, C, C, but I can commute, and so I can write it as a combination of operators of C dagger. Okay, I can, well, so what I'm saying is that you can rewrite this in terms of those U operators. And so what that means is that the Hamiltonian can be written in terms of the generators of this algebra. These are the generators of the algebra. The set of operators that defines this algebra, or generators. And so the Hamiltonian can be written in terms of those generators. And so one now can assume, well, let's try to put, and this is the case in fact, let's try to put all observables in terms of, write it out in terms of operators like C dagger alpha, C beta. Right? And so this is called the dynamical algebra of the problem. Sometimes it's also called spectrum generating algebra. And so the idea is that if you consider the generators of this algebra, all the observables, the Hamiltonian transition operators, can be written in terms of those generators.
So our Hamiltonian looks pretty, nice and compact as is. Why is it better to write it in terms of these U operators?
Oh, because then I make contact with this algebraic structure here. It's a fairly trivial business. Huh? So there is no, this has to do with this standard form to write the Hamiltonian, or the multipole form. The multipole form, if you remember, this was C dagger of A dagger A dagger A. Right? And that is precisely the form that is convenient here, because that shows explicitly that you can write your Hamiltonian in terms of the generators of this algebra.
But isn't our old algebra fine? The anti-commutation relations that we set up for our... Oh, I guess, well, these work for fermions or bosons.
Yes, these work for fermions or bosons, but the point is here, actually. This is the important point. If you look at the commutation relations of these objects, they close on the commutation. And so you can formulate everything in terms of the generators. But the transformation from C dagger C C to C dagger C dagger C is a trivial one. just a little bit of commuting. So that's not very deep. So you can use one representation or the other representation. They are sort of trivial. Okay. Now. Let me now introduce the notion of symmetry. General, so you assume that you have a Hamiltonian of your system. You have a number of operators which are called G. Suppose that these operators commute with the Hamiltonian, and that this happens for all elements, all transformations G. And now I'm going to use always capital G, and with this I refer to a Lie algebra, some Lie algebra. So in this particular case, G would be U omega, okay, and then the generators, so this little g would be all the operators U alpha beta. And so if this is the case, then one says that the Hamiltonian H has symmetry G. And there is a very important consequence of it. This so this I wrote on blackboard, so I don't have to go through it. This you can do this in general. Actually, you can define an object which is either a commutator or an anti-commutator, and you can prove that this will be false. And here, these are many particle states which are properly normalized. So this is basically also what I showed. Okay, so this is the proof that actually these Hamiltonians can be easily written as a combination of the operators U. This is the number of states, and here this is a little proof. It's maybe a little difficult, but the point is, so suppose that you have an eigenstate of this Hamiltonian, it has a certain energy. So now you're going to act with the Hamiltonian, you're going to create other states by acting with this transformation. Okay. On this state, okay, now H and G, by definition, they commute, right? So I can commute them through, and now H acting on this eigenstate, it has eigenvalue E. And so what I've shown here is that if gamma is an eigenstate of this Hamiltonian, the fact that the Hamiltonian commutes means that G of gamma, G acting on gamma, is also an eigenstate. So that's an easy consequence. So this immediately implies degeneracy. Because all states Gi have the same energy. Okay, now there is one last, this is sort of an algebraic concept that I would like to introduce. This is the notion of a Casimir operator. A Casimir operator is an operator which is associated with a certain Lie algebra. And so what I will use C for Casimir, then so it is associated with a particular algebra G, so that could be U omega for instance, or we will see other examples. And then it can have a certain order. Let's call it N. Okay? And this refers to the order in the generators. Right, so it can be linear and it's 1, and it's just a linear expression in terms of the U, but of the G, so the U alpha beta in this example. Or it can be quadratic or cubic. What is the property of this operator? That for all GI G, we have property that the Casimir operator commutes with these elements. Okay, and now you begin to see the connection between Casimir operators and Hamiltonian here. So this property, it implies symmetry, it implies degeneracy. And so this property is then, it seems to be associated with Casimir operators. These operators, they are known algebras, Lie algebras, they are classified. And so the classical Lie algebras, they are unitary. So denoted by U, orthogonal. Which are denoted by O or SU in this depends. And then the last, which we will also see in one example, this is related to seniority, is symplectic. This is SP. And then they have always a dimension, right? Omega in this case. And we will encounter examples of all three of them. But always I will try to relate these algebras with physical observations. Okay, and so now for each of those algebras, the classification of all the possible Casimir operators, this has been done in the 19th century, so this is established mathematical knowledge.
So you take some certain Lie algebra
Yeah.
and take these operators so that it could commute with all elements of this algebra. And what is the structure of this? I mean, if you take the set of these guys, what is their structure?
Of which guys?
Of the Casimir operators.
Oh, maybe I give an example, then you will say, it's trivial.
Yeah, because I don't get really. Is it like, what is?
Okay, let me give an example, which will be familiar to all of you. Okay, let's define the. No. Let's define the angular momentum operators. Look here at, let's say, orbital angular momentum. So it has three components, Lx and y and z. So this is a set. Okay, you know that, well, you can also write it equivalently, right, in terms of L plus minus Lz. And you know that these operators if they close on the commutation, you see this is this super z, then mz n plus minus this. Okay, so these satisfy the requirements of a Lie algebra, and it is a Lie algebra, and this Lie algebra is known as SO3. Why? Because these are related to rotations in 3 dimensions, so these are orthogonal transformations in 3 dimensions, so it's an orthogonal group, it's SO3. But it's an orthogonal Lie algebra, I should say. Okay, so what is the Casimir operator? You're all familiar with that one. It's just L square, that is Lex square plus L square plus LZ square. And you know, of course, that L square commutes with the triple commutes. So the L square is Casimir operator. Now it's squared here, so it's quadratic, so it's a quadratic Casimir operator. So this is a simple, it's probably the simplest example of a Casimir operator associated with it. Is that? Yeah.
So is there any way, given some arbitrary Lie algebra, to know what order the Casimir operator will be? Or do you just have to like guess a bunch of operators until you find it?
So, I mean, so it's just the order, right? But I guess the question is there any way of knowing what kind of orders are allowed for a given algebra?
Yeah.
As I said, this has been classified. It's not a trivial problem. I mean, this, I think it was solved by a Frenchman, Carton, in the 19th century. Okay? And the point is, of course, I can easily construct a quartic operator. I just have to square this one, right? And then I get a quartic operator, but that's not an independent operator. So it's what you're really after is how many independent Casimir operators you can construct for a given algebra. Turns out for SO3 there is one. For SU3, that's an important algebra in many applications, there are 2. And the number of Casimir operators is also related to the number of labels by which you characterize your eigenstates. So, you know, wave function, I mean, if you have SO3 symmetry, wave functions or eigenstates are characterized by the L quantum number. There is only one label, and that is related to the fact that there is only one Casimir. For SU3 you have 2 labels. You have a quadratic and a cubic. Okay, the only thing I will write here, and I will come back to it after the coffee break, is this formula. This refers to dynamical symmetry. So a Hamiltonian with the dynamical, we know what a Hamiltonian is with the symmetry. S. Now I write down here a Hamiltonian with the dynamical symmetry. It will be a linear combination of Casimir operators. Let me do it after the the transformations commute with the Hamiltonian. So if you have a rotationally invariant Hamiltonian, this Hamiltonian will commute with Lx, Ly, and Z. They form an algebra, so I wrote down the commutation relations for those operators. And so that means that the symmetry of the Hamiltonian is SO3, and the Hamiltonian can be labeled, the wave functions can be labeled by a quantum number L, and all the magnetic substates, ML minus L plus L, they are degenerate in energy. Yes.
So this statement here that H commutes with all of the little g's, does that mean H is also a Casimir operator on the group?
It's not. No, I don't think so, because H might have other.
H is not a component of G.
Yes.
That's
Because
not
that
the
would be
operator.
very restrictive. So that cannot be the case. Right? Because then there is only one choice. In this case, for instance, an H must be the Casimir operator. Okay, so there is only one, which is L squared. Clearly, you can have more. So it just says that well, I guess I should continue and try then to explain. But I don't think you can say that. Okay, so this is symmetry, dynamical, the symmetry algebra, the dynamical algebra. Right? This is just an algebra with generators. So this is a set of generators Gi. So in the case that I discussed, this was U alpha beta. And the only requirement is that all the observables can be written in terms of those generators. Like the Hamiltonian, we could write the Hamiltonian in terms of the U alpha beta. So a concrete example was this. U omega is the set of all the operators U alpha beta, and we could convince ourselves that the Hamiltonian can be written in terms of those generators. So this is the notion of symmetry algebra and dynamic algebra. It is certainly the case that in this case, so H is not necessarily commuting for all. Well, this is, I should really, misleading, but you see the point that in general, if you have an element of the dynamical algebra, it will not commute with the Hamiltonian. It does commute in the case of the symmetry. Okay, so now suppose that you have a classification. So this is a very large group. Right? If you want to know, for instance, the dimension of this group, the number of generators is omega squared. Right? So this can be a very large number, whereas we saw an example, the symmetry algebra, we just have 3 generators. So the number of elements of S of 3 is just 3. Okay, so this dynamical algebra is very much larger. It has very many more transitions than the symmetry algebra. Okay, so in general, you can find algebras in between them. And this will be discussed in many of the examples, for instance, in the IBM or in the shell model. You can look at intermediate algebras. And now let's suppose, so this is now the notion of dynamical symmetry, right? A Hamiltonian with a dynamical symmetry, right, will be written. So we have some coefficients, let's call them kappa. Then I can take arbitrary orders of Casimir operators, and I can take algebras which belong to this reduction. And here I have a summation of R. And so these are just coefficients. Okay. these Casimir operators. So this is a Casimir operator of order m. Right? So that means that if m is 1, it's a linear expression in terms of the generators of this algebra. If m is 2, it's quadratic. You also see that this has to do with the order of the interaction of the particles. Right? If you have one body and two body, one body single particle energies and two body interactions, then you should be able to write, you can take Casimir operators up to order 2, because this will correspond, this will give at most a two body interaction. And then the last thing here, so this is the Lie algebra. And an important thing of this Lie algebra, it should be belonging to this chain. So it should be 1 R, J, G2, or J symmetry, or whatever algebra that is in it. Okay. This looks like a little abstract, but especially in the lectures on the IBM, this will become much more concrete, right? And you will see what is the usefulness of this kind of expansion.
And R runs all over these groups
Yes. So
of this chain.
yeah,
Something.
if you want to write it explicitly, I would say R goes from 1 to P. I've called here the symmetry algebra the last one. And N goes from, well, 0 is a constant, so that's not interesting. So, but in principle, you have linear, and to a maximum, let's say the order of the interaction. Let's say 2, right? If you have m equals 1 and 2, linear and quadratic Casimir operators, you will have one body terms and two body interactions. Okay.
But what's the extraction is like we have some system that have some symmetries. So we look at these symmetries of this group of this system. Then we can start this symmetry group, and then we go over this chain up to the dynamical.
It's rather the other way around. So as I did, I define the dynamical group first, because I want to know.
But how do you know that when you look at some system, it's much easier to determine the symmetry group? No? The dynamical group is in it.
Well, the symmetry group, often it's also obvious. You know, for instance, rotational symmetry. This will imply SO3 isospin symmetry. This will imply this will be rotations in unitary transformations in isospin space.
And then you say, I take all the Casimirs operating in this chain,
well,
and construct my... not all, this coefficient will be 0?
Which ones?
This.
These can be arbitrary.
Even 0?
Even 0,
yeah.
If you wish, but that's not so interesting.
Yeah. And then I have some big Hamiltonian and try to solve it.
Well, let me make one more point, because I rewrite the Hamiltonian that I had. If you remember, I had this Hamiltonian in second quantization. Let's do it first. Then I can rewrite it in terms of my generators. Okay, these are coefficients, right? I mean, I don't care how they are exactly, but I can define it in terms of the generators. This is also a generator. This will be mu alpha alpha. Okay. So So everything is written in terms of generators. These are related to two-body matrix elements. These are related to single particle energies. So now, these are expressions in terms of the generator, so in terms of the coefficients u alpha beta. Right? So you will see that this is just a particular combination, particular choice of single particle energies and two-body interactions. It's very important to understand that this is the general Hamiltonian. This is, if you write a Hamiltonian with a dynamical symmetry, it's only a particular, this is a subset of all possible Hamiltonians over there. A subset. So I'm not claiming that you can do all Hamiltonians, solve Hamiltonians, all Hamiltonians with, that they all have a dynamical symmetry. This certainly is not the case. It's only for particular choices, epsilon and v, that you fall back to this kind of form. Okay. Now, what is the advantage of writing it like that? This can be expressed in one equation actually, namely, if you look at this property, Casimir operator of any algebra of any order belonging to that chain, you take the commutator of any other Casimir operator, of any other algebra, this is here. This is, we can prove, this is based on the fact that these are Casimir operators, they commute with all the generators of the algebra GR. This property can be proved. This is an exercise definition. What is essential is that all the Casimir's operators must belong to a particular reduction from the dynamical algebra to the symmetry algebra. That is essential.
Yes, I missed something between the order of the Casimir operator for SO3.
Yes.
Because for me, Angular 1, 2 is act on one body. And you say that the order of the Casimir operator depends on it's one body or two body interactions.
Okay.
So,
So, because I gave the example here, what was the Casimir operator in this case? The Casimir operator was C2 SO3. Okay, the SO3, it was because it's written in terms of the generators of Lx, y, and z. And the 2 here, the quadratic, it comes from the fact that you have Lx squared and y squared plus z squared. Okay. And so you can look as much as you want, but there is no linear Casimir operator in SO3. So because Lx does not commute with Ly or you can only define a quadratic Casimir operator because that's the only operator that commutes with Lx and y and z, all of them.
okay, so the order of M of
Yes.
the Casimir operator is not necessarily due to the interaction between.
No, this will be given by the Lie algebraic structure. But what I meant is that once you have an order here, it will impact on the order of the interaction that you have here. It's clear, if you have a linear Casimir operator, it exists, right? Then it is linear in U alpha beta, and so it must, in the end, reduce to a term of this kind. Yes.
What are the Casimir operators of our U omega?
There are none, actually. There is a little, I mean, this is a technical thing. Well, no, I should say, well, let me not get into technical, because this is, technically speaking, it's not a Lie algebra, it's not a classical Lie algebra. You should also only look at SU omega, but forget about that. But the linear operator here very simple. Right? It is alpha u alpha alpha. It's the sum. It's the number operator. Right? This, remember, this will be C alpha alpha. Okay, and I think this was the next. This you showed somewhere, and to show that here you count the number of particles. Okay, and so it's rather easy to show that the number operator commutes with all linear numbers. So the linear Casimir, there is the linear Casimir operator of u omega is just a number operator. Okay. Yes, that's it. But to define the labels, as I said, I made this comment that the number of Casimir, independent Casimir operators defines the labels associated with algebra. This is only true for the classical algebras, and this is strictly speaking not classical. So, okay. This means you have now expressed your Hamiltonian in terms of set of commuting operators. And then from basic quantum mechanics, you know that you can solve this Hamiltonian. So you see many examples. And so let me.
I have a question.
Yes.
Why we are taking Casimir operators until quadratic order? Or in this case could be...
This is maybe, I should give no opinion. There is no fundamental. I just put here a 2 that if you want to go only up to two-body interactions, then you stop at 2.
Okay.
Okay. But there is no fundamental reason. So this technique can be applied to higher order interactions.
Okay, that's fine.
Yeah, let me summarize. So this is here. This I would call algebras that break the original dynamical algebra. And then in the end we have something which is associated with the symmetry. I think you see you have here a Hamilton to answer your question, but this is only the Casimir operator of. In this example, if the symmetry algebra is SO3, right, it's clear that you have more Casimir operators than just the quadratic one of SO3. Right? So you can write your Hamiltonian. It has a much richer structure than just L squared. But still, if it commutes with Lx and Y and Z, then SO3 is the symmetry. So here, typically, so this will be U omega, and so the associated formula is just as I showed here. It's associated with the number operator, so this will be the number of particles. Here, this I've already mentioned several times, so let's suppose that this is SO3, then the associated quantum number is the angular momentum, right? And the symmetry implies that all the states ML, right, all the magnetic substates are degenerate. And here you have, in general, that is the nice thing about this dynamical symmetry. So you have a quantum number associated to each algebra. It's intermediate. Let's call it, I don't know, C. So you can now define a number of labels in addition to angular momentum, in addition to particle number, a number of labels. And these labels, they allow you to classify your states, to find selection rules and things like that. This is not the only example of symmetry algebra. So this is okay. Another example of a symmetry algebra, this we will discuss, is SU2 associated with isospin algebra SU2. So this is one example I will discuss immediately in detail. There is one additional feature which is nice. So this is dynamical symmetry. And so what the features are, all the eigenstates are solvable. So you have a simple energy expression for the energy of all the eigenstates, the entire spectrum. So even if you would have 1,000 particles here, you can get an analytic formula for the energies of the eigenstates. So maybe I should all eigenenergies are known analytically, let's put it that way. So you will have eigenstates are solvable. And this is perhaps the most important property. The wave functions have a fixed structure. What do I mean by that? So you have a number of parameters, coefficients in this Hamiltonian, right? Now, in a general case, if you have a Hamiltonian like this, with single particle energies, two body reactions, and you change the values of those coefficients, then the structure of your eigenstate changes. Okay, that is general feature. Here it is different. So you change the coefficients here, nothing happens to the structure of the wave function. The wave functions will remain with the same fixed structure. We will see several examples of this in the exercise sessions, how this works out. So this is a very important property because this immediately leads, since the wave functions have a fixed structure, they do not depend on the coefficients in Hamiltonian. This immediately leads to selection rules. Okay? Because you work out transitions between levels once and for all, since those wave functions do not depend on the parameters in Hamiltonian, they are valid entities. Yes?
What is the physical meaning of the selection rules from the dynamical symmetries? Or what we can say about them?
The physical meaning, see what we will try to do for selection rules. I mean, this is getting ahead a little. I mean, we will discuss some example which is related to E1 transitions. But you need to construct observables, I mean, for instance, you have a transition, okay? Associated with this is an operator. I assume that this operator can now be written in terms of the generators of the algebra. Okay? If that is the case, then this is correct to call the dynamical algebra of the problem. You can describe it within that algebraic structure. Then you will now introduce this operator and try to calculate the matrix elements between wave functions that have a fixed structure. Okay. And this can be done independently of whatever parameters you have. We will show an example for Iwan transitions in nuclear energies.
So, I just wanted to ask, are we going to do this in practice? Like, we just have some system?
Oh yes.
So I mean, the general idea is, okay, I have some system, and when I have some system, I can just think about, okay, it has this and these symmetries. Then I should get a dynamical group that goes into this chain and ends up at this symmetry.
Yes.
And hopefully, when I get the Hamiltonian with some coefficients.
I think we will do nothing else than that actually for the remaining two. Well, a lot will be like that. I mean, so at least the lectures of Jan Joly, Rick probably also will discuss the idea. This is precisely this kind of idea one will follow. I will give a lecture on shell model, and so I will also follow this idea of defining symmetry algebras, dynamical algebras, looking at breakings, defining the quantum numbers associated with it, etc. So let me just, because this is well known from the interacting boson model, right? Where this is U6 and this is SO3, and most people will have seen something about that. But this also happens in the shell model. So in the shell model, you can discuss things in a similar way. So let me just, maybe I have. So I will discuss in a moment isospin symmetry. There is also there is a relation with seniority, and I will discuss my lecture seniority in terms of, well, this is SU2, but you can also show it's associated with the symplectic algebra, so I will go through that in detail. There is the interactive boson model, as I said, so there the dynamical group is U6, the symmetry group is SO3, and the various breakings are here, and these are the physical features associated with these breakings. This we saw already. So lectures of Vic. And there is also this I will also discuss supermultiplet, which is a very old model by Wittmer, and especially important is SU3, because that is an explicit model where you show that within the spherical shell model you can get rotational features. So this will also probably Mark Caprio. I should say that one of the lecturers has arrived, which is Mark Caprio, which is sitting in the lab. So he certainly will discuss rotational features in a shell model. So that will make contact with the idea of SU3. Okay, yes.
What determines whether or not there's a G break?
It's essentially a mathematical problem originally. So when one can use this, right? So if I understand the question well, let's do this for U6, right? We know we have S and D bosons, so the dynamical algebra is U6. We want to construct Hamiltonians with a rotational invariance. Okay, so you have to get from U6 to SO3. This is a mathematical problem. The different ways how you can get from not so difficult, but some extensions. And I should say that there is a connection, for instance, between SU3 in Boson model and SU3 in shell model. And this has been applied, for instance, in the SV shell. Okay, and this applies to SND boson. So you see that there is some relation between them. They're not identical. There are at least relations. Let me discuss an example to isospin symmetry, and we'll spend some time on isospin, because this I think is a difficult concept. So here it is written. So this was something which was suggested a long time ago. Heisenberg in 1932, Wigner in 1937. And so what are the empirical observations? I mean, you have about equal masses of the neutron and proton. They both have spin 1/2. And neutron, proton, strong forces are similar. They're not identical, but they are similar. And so these two features led Heisenberg to propose this idea of isospin symmetry. But the equality of the interactions is also an important feature that was stressed actually by Wigner in this later paper. Okay. So the idea is we define two charge states of a nucleon. One zero. So this would correspond to a neutron. 0, 1. This corresponds to. Okay. So the idea is now, if there is isospin symmetry, then you can rotate in this isospin space and transform to unitary transformations in this isospin space, and the Hamiltonian should be invariant under those transformations. So that would be the definition of a Hamiltonian which has isospin symmetry. It is invariant under those transformations. It commutes with the transformations between the different isospin states. Now, how do you write in general such a transformation? And this is one way of writing it. There is, in my notes, there is a sort of a more lengthy derivation of this equation, but this is a standard derivation. So I will put the notes on the website just after the lecture. Okay, so these are the Pauli matrices. Okay, so these were the matrices introduced to discuss the spin of fermions, spin of half fermions. And so you see the derivation which is given in the note shows that the isospin transformations are completely identical, at least mathematically, with the Pauli matrices. Okay, so you have three matrices. Let's call this Tx, Ty, Tz. Okay, and then we can define combinations T plus minus Tx, T plus minus Ty, and then we can show the basis of these commutation relations that T Z plus minus T plus minus T plus minus and plus okay, and so now the action is you can show with the explicit matrix representation and with these basis vectors. It's quite logical. For instance, if you the convention is that the neutron is isospin up and the proton is isospin down. So if you want to increase the isospin of the neutron, for instance, the neutron state, this gives 0. The minus of the neutron is the proton Tz. Plus Tz over proton minus. Okay, so this is easily derived by using the matrices here.
So
okay, this yeah.
what are Ex, Y, and Ez? I don't know.
Oh. This is just a conventional factor.
Yes.
But these are the parameter. The idea is, you see, the idea is you have transformations, unitary transformations between these states. Okay, this is an infinite set of possible transformation because they depend on continuous variables. You have continuous transformations. And that would be actually, those transformations would form a group, a Lie group, right? They depend on continuous parameters. Here, it is much simpler because you see now I can write any transformation in terms of infinitesimal transformations. These are small numbers. Right? So I have an infinitesimal transformation times dx, an infinitesimal transformation times dy, and an infinitesimal transformation times dz. And this is the most general infinitesimal transformation I can do. In fact, from those tx, ty, tz, and suitable parameters, I can generate all possible transformations. Right? So this is the idea of a group versus an algebra. A group would be all transformations, whereas an algebra is confined to infinitesimal transformation, but you see here it is infinitesimally different from just the identity. And so you have the identity plus a small transformation. There was another question. Yes.
I was going to ask the same thing.
So, this, I guess, for one nucleon, this is none. Right? So what you have to do now is to, then it becomes more difficult, to apply this to A nucleons. now I use capital. I will not write x, y, z or z equals to minus repeatedly. I just will give it an index mu. So mu can be minus 1, 0, plus 1. Okay. And what is for an A-particle system? My isospin operator is you have a summation for all the particles, and then you have the isospin associated to particles. Okay. The T mu's are defined in terms of those. Okay. So, now we can formulate the question of isospin symmetry. So what does it mean? Following the terminology we introduced just a minute ago. We have a Hamiltonian that commutes with the generator, the isospin generator. So remember, this is a Hamiltonian with decayed particles. So now we can assume, and this was assumed by Heisenberg Wigner, that the nuclear Hamiltonian commutes with the isospin generators.
Excuse me, but minus 1, 0, plus 1, you mean x, y, and z?
Yes, well, or combinations of them. So these combinations, yeah, I think there is maybe, I could have a factor square root of 2 here. So there's one over the square root of 2.
So by T0 you mean TZ?
TZ.
And, okay.
Yes, yes.
Okay.
This you shouldn't take, I shouldn't check that, but I think it's 1 over square.
Just some labeling. That's really nice.
Okay, so what is the property of the Hamiltonian that is isospin symmetry? So now we can apply our rule, because these are identical commutation relations as for SO3. Or for some reason this is called SU2. I don't want to get into that, but the algebras of SU2 and SO3 are the same. The point is that for SO3 I had integer, so I was talking about orbital angular momentum, so integer value. Here I have spin 1/2 object, so the representation can be half integer, and then one has to use a terminology SU2. And I will talk here about SU2 and then put an index T to remind myself that this is the SU2 algebra which is associated with isospin. Okay. Because, yeah, this I should have said, that these T, capital T's, so the many body, the ones that act on all the particles, they're exactly the same commutation rules as the individual T's. Okay, so let's suppose we have a Hamiltonian with this property. This will be approximate, we know that, because the Hamiltonian, of course, is also, the nucleus is also protons, and we have no interaction between the protons, but not between the neutrons, so certainly there must be some difference in the interaction between the two, so but let's forget about that for a moment. Then I have eigenstates, right, which will be characterized by a set of quantum numbers that I don't know. This could be in the angular momentum, its projection, but certainly I will have a quantum number isospin in its projection in T. And all the states with mt and minus T plus T, they are degenerate. So this is the property of degeneracy that I mentioned associated with the symmetry. So I have T squared this equals 1. Tz empty. Now, this is easy to understand what it is. Tz, so it's just a sum of these operators. This Tz operator is a property that it gives 1/2 of a neutron and minus 1/2 of a proton.
So this isosymmetry, I guess I'm a little confused because the binding energy of 100 neutron ball is different than the binding energy of 100 proton ball.
Yes. Yes.
By a lot, right?
I will come to that. So this is, yeah, you would think this must be a terrible approximation, right? I mean, this cannot be true because there is this huge binding energy difference. It turns out that actually the quantum number is reasonably well conserved, even notwithstanding these huge differences in binding energy. These are mainly diagonal shifts between the two without affecting the waveform. So you make contact with this idea of dynamical symmetry, where you split states, but without changing their structure. Yes. Yeah. Well, okay.
It's just another question. I was so there is no h bar square or h bar factor in those. I was wondering.
No.
No. Just
It
be
is,
sure.
it's formally equivalent with angular momentum, but
It's not exactly. No.
Apart from the difference between the proton and neutron energies, there is also a point that neutron is not stable, and proton, yes. How it can be put in this framework, that you have annihilation and you have operators which can create or not a proton or neutron from a proton or neutron. I don't know. Can we plot something which breaks this symmetry, or
related to the decay properties of the particles. That's your question.
Yes.
I don't know, but basically the decay property comes from the mass difference. Yes. So it's just that one is higher than the other, so the neutron decays.
Yes, but my point is,
and that can be put in rather easily.
Yes. But in the description, it seems that neutron can become a proton and vice versa in the same way.
Yes.
But it's not the case. We should just consider neutron and proton in the vacuum. So.
I'm not sure. I mean, a beta decay operator, so would transform beta plus beta minus a neutron into a proton or proton into a neutron. So certainly you can describe beta decay with these operators. Well, Fermi beta decay. So you just change the neutron to the proton or vice versa without changing the spin. That can be modeled by these operators. Well, but it's in a many-body context, so I don't know about one, the decay of the neutron. You can also have gamma thermal decay, and you change the proton into a neutron or vice versa, and you change the spin. This requires some modification, but you can also discuss it algebraically. Yes, I was saying here, so you get plus 1/2 of a neutron minus 1/2 of a proton. So you act, right, on A nucleons, N of them are neutrons, Z of them are protons, so you get something N Z over 2. Okay. And so Tz is actually always, or MT is always a good quantum number. Right? It's just the difference between neutrons and protons. is some, how to say this in English, abus de langage.
What?
Abus de langage. Abuse of language, let me give
Oh.
People often talk about N minus Z and they immediately associate it with isospin. It is, strictly speaking, it's fine if you know what you're talking about, it's okay. But strictly speaking, it's only the Z component of the isospin which is meant. Okay.
Yeah, but you cannot say that it's conserved if you include pairing.
This empty is always conserved.
I mean the particle number. You said particle number is conserved.
Oh, yeah, but that is a defect of the theory.
Yeah, I know that.
So I know. I mean, there are of course ways to solve where you do not conserve particle number, and then you have a problem with the T. I agree, but that's a problem of the theory. I mean, the reality has, well, as far as we know at the moment, there is charge conservation. So this will be the conserved quantum. Yes, but you're right. I mean, yes. If you discuss isospin symmetry and isospin PZ symmetry in the context of a model, you might have a model where this is not conserved. Yes. So, okay. Okay, so as it was remarked already, we have a Coulomb interaction between the protons, and this will strongly violate this degeneracy. So can we now make an estimate of how to treat this in this context? So there is, I should say, there is also, of course, an isospin violating component of the nuclear interaction. But let me give the argument with Coulomb, because we all know. So the interaction. Okay, we know, so you must have DZs done for the two particles in order to have interaction. Okay. So now you can do something, you can do decomposition, tensor decomposition in isospin. This I will try to explain, because that's this one trivial thing, of course. That you just write this out, one fault, and then okay. really concerned about this expression. What does it mean? Okay. This is a constant, so it's a scalar. This is a vector, so it's the z component of the isospin vector. Okay. So, but what is this? And it turns out that you can write this here. This is the notation I used to evaluate. Okay. The important point, this is a difficult point, people struggle with this. Isospin, so the Coulomb interaction has a scale, an isoscalar, an isovector, and an isotensor component. So why does, because this is confusing, people sort of say, but my nucleus has spin 1/2. So if I put two nucleons together, how do I get the tensor? How do I get lambda equals to 2? Right? How does that come about? But you should remember, this is a vector. So this is an isospin vector. So it has three components. It has z, it has x, y, or plus minus. Right? And so the vector you can couple, of course, to 0, you can couple to 1, and you can couple to 2. So there are the three components of the isospin of the Coulomb interaction. So it can be scalar, vector, and tensor. If you would like to think of this in second quantization, this is another argument. Right? So if I forget about all the labels, but I just label my particle with the isospin quantum number, okay, then indeed I have a creation operator.
Sorry?
Yes?
Can you explain again why tzk is a vector?
Because it has three components.
For me, it's the z component of
No,
a vector.
what I mean is the third component of a vector.
But
Okay.
that one is a scalar then. A component of a vector is a scalar, isn't it?
No, but if you do a transformation in
You
this
can get the
space,
others.
you will get to the other components. Okay, so let me repeat the argument, but in a different way. So you have particles, creation operators, so you have isospin 1/2. They have two indeed. This is a spin, an isospin 1/2 object. Okay, but now to create the isospin vector, what I call T associated with a particle, with a certain particle, this you construct in this way: 1/2 coupled with the annihilation operator. I put it here, and this is coupled to 1. Okay? It has three components. Okay. So here you see you take a creation operator and an annihilation operator, and this is a vector. And now you see that if you take two vectors together, so you have an isospin 1 object, you can couple to scalar vector. So the three possibilities. Now it's a technical matter to rewrite this. This is a scalar, right? That's obvious. This is a vector. I mean, this is a component of a vector. That's also obvious. This is a bit more difficult. How to get this? I can give you the results. Then you can struggle a little trying to derive it. So I hope I convinced you that you have the three components available. So now, I should perhaps indicate here what is the projection in isospin. The projection is always zero. This is what you said. The z component of a vector. So projection, you don't change. The projection is associated with particle number. This interaction doesn't change anything about particle number, so the component here is zero. Okay, so let me now write the expressions. I will be buffering a little bit, but it can be shown. This is basically getting this from Clebsch-Gordan coefficients. So you couple this two angular momentum 0, and we take the 0 component. And then you have here always the same factor, which doesn't interest me. Okay, so this is the scalar part. The vector part. This is trivial because it's exactly here. So Z component. Okay, times the same factor. And then we have the so this is isoscalar.
There is no vector part coming from the tensor component.
Excuse me?
There is no vector part coming from the tensor component of the Coulomb interaction.
This I don't understand as a semantic question. I have a problem with.
Okay, like have a look at the isovector part now.
Yes.
Yeah, and we've got the component. You added these two vectors, yes?
Yeah.
And is there no component of product of these two t which should be added?
This is here.
Yes.
Oh, I see. No.
This is 0.
This is 0. Yes.
And why?
Well, it comes from Clebsch-Gordan coefficients. I mean,
okay.
Yeah. This will take me some. Okay, I can. But it's basically what you want to do is to. Yes, it is a good question. So you want to do this kind of problem, and you copy it to lambda. And if you look at the 0 component, because there was 0 component, and you write it out for the different lambdas. And then you try to fix with Clebsch-Gordan coefficients. Right? And then from these combinations you can derive these results. But you're right, yes, it's not obvious. Okay. Time is 6. Yes, I probably will do this because I would like to discuss one more thing which is very useful. This is the Wigner-Eckert theorem, and we have a beautiful application of the Wigner-Eckert theorem from this. So this is our two-law interaction. We have written it as a components isoscalar, isovector, isotensor. Okay. So now we're going to use this in a basis which defines in this way. So the idea is we have a Hamiltonian which conserves symmetry, isospin symmetry. To this Hamiltonian we add the Coulomb interaction. Okay, this we consider as a perturbation. And so now we will calculate matrix elements in first order perturbation theory. So I had states which were I have my lambda here, 0 components. I'm not going to write the summation of the particle indices, and I want to calculate this kind of matrix. Okay? And so now I can do something neat. I can say this is characterized by spin isospin projection. This I have decomposed. So I have looked at the character of the interaction and decomposed it according to its transformation properties in isospin space. And I found out it's either scalar, vector, or tensor. And here again I have EMT. Okay. And then this is multiplied. This is already mentioned by Rick, by a reduced matrix element. This is a reduced matrix element. And the reason that you can do this is due to the Wigner-Eckert theorem. Okay. Let me first say something about the general structure. You see here you have a matrix element that depends on T and MT. Okay. The MT dependence is now completely removed from this reduced matrix. Okay, so the MT dependence is completely contained in the Clebsch-Gordan coefficient, and which is multiplied by the reduced matrix element. So what it means is you have to calculate this matrix element of one choice, particular choice of MT, right? Whatever is most convenient, and all the others follow. The other thing I should mention that there are some different conventions for this reduced matrix element. Some people will put here instead of a Clebsch-Gordan coefficient a 3J symbol. So then you have some factor which comes in 2 T plus 1 or whatever. So that the basic structure or the basic idea doesn't change. This is very important. So this is an illustration of it in the context of isospin. It's probably more familiar to all of you in the context of angular momentum. So let me just write the equivalent thing for angular momentum. So for angular momentum, I have the same kind of, for instance, you have a transition. Let's talk about something where you have an initial state characterized by angular momentum Ji, which is a transition, maybe an electromagnetic transition, whatever, to a state which is characterized by final angular momentum Kf. Okay, so you need this kind of process to calculate the matrix element this time. Right? So here you have your transition operators. Lambda, U, there is the I, Mi. It's conventional to put here the initial state. The operator acts on the initial state to give the final state, and so the Wigner-Eckert theorem tells you this will be equal to lambda mu Jf Mf times the reduced matrix. Okay. So what you should realize, just some side comments, that this is a general mechanism. Okay. So in this example, this was something which is associated with SO3 here is the ensemble of Jx, Jy, Jz. SO2 is just the Jz operator. So the associated label operation. This is reduction is SO2, which is just one single generator. The associated label here is diagram J. Here it will be projection M. Okay. And so you see this has associated with it a Wigner-Eckert theorem where you factor out the dependence of this guy. And actually, this is a general mechanism in terms of two algebras. So, this is a side remark, but this just to tell you that this is a very powerful theorem. It can be generalized to many algebraic structures. Right? So now, as we will see during the coming days, if you have something which corresponds to a chain of algebras, you have labels associated with them, so you can likewise consider situations where you have an initial state characterized by these labels, then a transition operator, which and then the final state here. This can always be written as some kind of a generalized Lectures coefficient. Times the reduced matrix. I'm not going to use this, but I just would like to mention that this is so the same kind of mechanism. So here we have a reduced matrix element. Here it depends only on the properties of the large algebra. We have here generalized Clebsch-Gordon coefficients. Suppose we can calculate those generalized Clebsch-Gordon coefficients. Then we can calculate, we only have to calculate one matrix element here, and we have all. This is a general applicable theorem. So this Wigner-Eckert theorem. So what I did there is to apply it to the case of, again, this was SU2 to SO2. Right? So this is SU2 associated with isocycle, and SO2 associated with projection.
Can you write down the definition of this generalized reduced matrix element? Just the
It follows from this relation.
right. So I mentioned, is it just the same as the angular momentum reduced matrix element, but replacing the labels with these general labels?
That not. The question is about.
Well, right now we've just written this reduced matrix element, but how is it defined? Like when you unpack it?
Oh, it's defined through this equation. So there must be a way to calculate at least one of those matrix elements. And if you can do that, and if you know the Gaussian coefficient, well, in this case it's just an ordinary Gaussian coefficient you know, then you can deduce the reduced matrix. Okay. Is that clear? Or?
Yeah, it's still not quite what I'm asking. Like normally, we can just write out the reduced matrix element, like the definition of it, right? Or no? Am I crazy?
Because you can have all these matrix elements with these m projection quantum numbers. Like you calculate just once for one quantum number, then you can have whole matrix elements just because of this formula.
Yeah.
So, yeah.
Okay. I said more being, so I would like to get to the.
Could use the example in the bottom line. You have gamma in parentheses, big gamma and which is, yes, you have the two gamma on the operator T.
Yeah.
When you look at the on G, there we have lambda mu, which refers also to G and N.
So the lambda here, this refers to SO3. The mu here, this is the projection, it refers to SO3. And I stress this is all a side remark, so you will be maybe baffled by this kind of. And even you can do it. This can be shaped algebras, and then you can decompose this algebra. Let's go to coefficient. Okay, so now I come back to here. Okay, so this in the scale. It must be empty. I don't know. It's linear. The vector the tensor, sorry. The tensor is organic.
That's the line.
Excuse me?
That's the line.
So now we have derived this matrix element in first order perturbation theory. And so in first order perturbation theory, we have states with energies due to the Coulomb, right, which can be written as a constant, plus something which is
Well, these coefficients, they depend on n eta, any of the quantum numbers, and also on isospin. So this must have seen maybe somewhere. So this is known as the isobaric mass. Which was proposed by Wigner. So so you get this equation just by looking at the isospin decomposition of the Coulomb interaction. This is first order perturbation. This does not mean that the Coulomb interaction will not break isospin symmetry, because of course, if you look at this matrix element, now I take lambda. Well, I convinced you that the empty on the left and on the right, that will be conserved. But this, in general, is different from 0 if t prime is different from t. And this, from the well, if it's a scalar, of course, it cannot change t from t prime. Okay? So the scalar contribution of the Coulomb interaction, which is the bulk, actually, this is the most important, it will not change the isospin. So that will be isospin conserved. However, the isovector and the isotensor, they might change isospin. So this is in general different from 0 for lambda equals 1.
So, can I ask a question about, so if I take some isobars and start plotting their masses relative to each other, would they follow this formula?
Yes, to a large approximation.
Do you have a slide with these things?
Yes, I can show. That will be actually the last thing to show. Right. So these are examples of isobaric multiplets. So this is, right, so the mass of the two, I hope this is visible, but the mass of the two is 49. Okay, so this is chromium 24 protons, 25 neutrons. Here is the inverse, so these are mirror nuclei. If you just do the counting or in terms of isospin projection, so this is mt plus 1, mt minus 1 half, and look at the spectra, so this is the experimental spectrum of the two nuclei, and what you say is true, so there is a big shift between the two, right? And that will be increased if you make the difference.
Well, no, I mean, shouldn't we do this with like a bigger isobaric chain?
Yeah,
so we will see some parabola, or not parabola, but
yeah, I will show in a moment. So first I would like to discuss a simple case. Okay, so you see that the spectra are very similar, although they are displaced in energy. Okay, this inset here shows the differences in excitation energy as a function of spin. And you see these differences are not larger than 100 keV. Okay, so that means that energy in both spectra are. But let me come to an example of a multiplet. Multiplet, this is another example of a multiplet. This is a multiplet. Right. So this is A equals 32. Right.
Okay, so this is a quintuplet. Right? So this is equals 2. Okay, t equals 2. So mt of n minus z over 2 goes from minus 2 to plus 2. So you have 5 nuclei in the quintuplet. They are here. Argon up to silicon. So argon is what is there? 18. So MT is minus 2. Okay, because we have more protons and neutrons. And then, of course, necessarily, T must be 2 or higher. Right? But the ground state will be the lowest possible T, which is compatible with MT. Okay? So this is one extreme. The other extreme is silicon. So it is MT plus 2, E2. But then you see also it associates states. These are excited states in chloride, sulfur, and phosphorus. Okay, that's important. So the ground state of sulfur here, sulfur is 16. So it's 16. It's an M equals Z nucleus. So the MT is 0. So the T in the ground state most likely around this, I think it will be 0. Okay, for any positive, no, it's even neutral, so it's 0. But then you have also in the spectra T equals 1 and T equals 2 states. Okay, so this is an excited state, sulfur, but it belongs to the same isobaric nucleus. So if I would apply 0 plus
1, sorry.
So
It shouldn't be, I just mean for the ground state, shouldn't be 1, like in order to have angular momenta 0 for the ground state.
but I'm discussing the T equals 2 states. I agree
Yeah,
with you.
I understand, like I mean to have, in order to have the ground state of this nucleus 0,
Yeah.
angular momentum 0, then you should have isospin 1.
Oh, but this is for you protons and neutrons. So I understand your question. So if you have two identical particles coupled to 0, then of course you have T equals 1. But here, well, already it's difficult to talk here about two particles, but there would be a neutron and a proton. Yeah, no, I think no, you cannot look at this as a, what would it be, so one nucleus plus a neutron and a proton. You're right, if you look at N equals Z nuclei which are odd, then you don't know in advance whether the ground state is T equals 1 or T equals 0. That is, but these are the only nuclei where there is some question about it. For all other nuclei, the ground state isospin is always empty. Always. Sorry. That's an empirical fact. But so the ground state of this nucleus will have will be 0 plus. Okay, so you're looking at excited 0 plus states in sulfur here. The energy is really tens of MeV, I think, right? Because this is T equals 2. Right? But the structure of that state is very similar to the structure of the ground state of argon. Or the structure of the ground state of silicon.
And you go from, these states are connected by these T plus operators. And so if you act with T plus on argon, which you get to this excited state of chloride, then you get to the doubly excited state of sulfur and so on. Okay. This so this is an example of a quartet. So with half integer isospheres.
And is this examples a little bit filter out, or you should take it for any set of isobars you'll get that?
Yeah, this works rather well.
So isosphere is very good symmetry for us.
I don't know whether that is a conclusion you can draw from this, right? You can only say, well, this is sort of a formula that works, right? But this is not really a test of to what extent that this is a good continuum. Let me show you one more, and then I stop, right? Because it's 33 already. This is, you see, this is C3. C3 would be in this notation here, kappa term. So, you see, you can fit now all the isobaric multiplets that are known and see whether there is a third here, a cubic dependence on MT or not. And you see that most of the multiplets that are here, so you see for each point, this is a set of nuclei, like this, each point is a set of nuclei where you have fitted such a formula. Okay, and you see that most of the nuclei are consistent with coefficient C3 or kappa 3, which is here. Okay, I think I will stop here. If there are urgent questions, you can ask them now. Otherwise, we have the afternoon.
Which is the common way to determine which symmetries are involved in the nuclei?
The common way.
Yeah.
Could you be maybe more precise?
Because sometimes, okay, I know that we try to identify the degrees of freedom of the system, and we can associate sometimes symmetries, but not always works, because sometimes the symmetry is not is always strict, and when we want to determine energies or another quantities, doesn't work the model. So what we can infer about that?
Well, I don't know whether I can answer this satisfactorily, but I would say the choice of your dynamical algebra, that has to do with the degrees of freedom, right, that you want to include. But of course, this is a physics choice. Huh? And like IBM, you say, well, I have an S pair and a D pair, and that is the most important degree of freedom for my model, and then we could include that. But you might do octupole or whatever. Okay, so that defines your dynamical algebra. Rick has a better answer.
Better. How do you know it's better? No, I have a. Maybe I understood the question a little differently.
Oh, okay.
Suppose you talk about dynamical symmetries.
Okay.
Okay, you have this chain of groups. Each group in the chain defines a certain quantum number, which is associated with the levels, and there's an energy expression, an eigenvalue expression, for how the energy should go as a function of that quantum number. And so you have a nucleus, you look at the energy levels, the spins, parities, and so on, and you ask, does it look like one of these symmetries? Does it satisfy those equations?
Okay.
And in general, it won't, because these group theoretical descriptions tell you what a nucleus can do, but not whether any given nucleus does it. And so if it does it, if you're lucky, then that's great. You can assign that symmetry. If it doesn't, you can look to see if it's close to that symmetry, close to those analytic formulas. And if it's close, you might take the Hamiltonian and add some terms that break the symmetry and then diagonalize it and see if you can do better. Is that an answer?
Okay. So
Thank you.
I what is that C3?
C3.
Is that what you were
Yes.
asking?
Yes, yes.
I derived here this, but then so you would people then, I mean, this is sort of a phenomenological formula. They say maybe there is a three-body, well, which could come from a three-body, right? So maybe there's a cubic contribution in a cube, right? And so kappa 3 is just C3.
Ah.
This is
So, what is the meaning of this?
the meaning of this is that you can forget about kappa in most cases, right? And I think there are few exceptions with this one. This is a bit of an old one, this one. There are a few exceptions. But you see, this formula assumes that you have exact isospin symmetry. Now you might have two levels with different isospin, but with the same spin. They can mix, right? And they will repel. And that will, then this formula will be violated. Right? Because this can happen in one nucleus, but then in another nucleus, this doesn't happen anymore. So that means that the structure, in the isobaric multiplet, the structure of those nuclei here, just for the picture, then we should stop. The structure of those nuclei is very simply related by these T plus operators. If now we have levels that are close and mixing, then of course these relations will be violated. They're not simply connected anymore with T plus. And then this kind of formula will not work anymore. There is no fundamental, that's true, no fundamental reason to say to add a cubic. Okay. Should we go and
Well, just simple question. You were arguing on the basis of Coulomb interaction, right?
Yes.
Now there is the strong interaction part in the isospin breaking. Is that capable of generating higher empty terms?
Yes. I guess if it is three-body, then
No, but on the level of cubic two bodies, strong interaction in general two body strong interaction, not Coulomb one. Can't you get higher empty terms than square?
if it is two-body, you can make the same argument, and the highest is a tensor. But that excludes things like mixing between levels and things like that.
Yeah.
And this is a good point. Actually, you might say, well, we know the Coulomb interaction, so why do you do this? Okay, but one of the points of this kind of analysis is trying to disentangle effects of the Coulomb interaction from effects of isospin breaking nuclear interaction. That's still an unresolved question.
Could I make one comment? I promise it'll be less than 1 minute. Actually, two comments. When he talked about sulfur there and said that the levels will have a similar structure up and down the multiplet, a nucleus like sulfur will have other states with T equals 0, T equals 1, which are completely different than those of argon.
Yes.
So it applies to a subset of states that exist in argon. The other comment is when you made this remark down at the bottom of the blackboard there that the wave functions don't depend on the strengths of the interactions, which may seem strange. I just want to point out that in the first afternoon, you calculated an example of that We calculated the wave functions for two degenerate levels with an interaction of 10 kilovolts and 100 kilovolts, and the wave functions were unchanged.
Yes, you will see many of them.
You'll see. Yeah.
Okay. But it's an important point, so it should be repeated. Okay, let's have lunch and then exercises.